Okay, now we are going to the last section of this chapter, electrical power. Um, so let's share the PowerPoint. And if you recall, you may not recall, way back in chapter 8, we had a general equation, an expanded equation for the conservation of energy, which was delta K plus delta U plus delta E internal is equal to WQ, then a whole bunch of T's, where W was work, Q was heat, and then all the T's were transfer mechanisms, mechanical wave, matter transfer, electrical transmission, and electromagnetic radiation. And so we're going to bring that modified form of that in this first equation. The internal energy is equal to heat plus electrical transmission plus electromagnetic radiation. That's the equation that we're going to use. It's a conservation of energy. So the diagram says the direction of the effective flow of positive charge is clockwise. So the internal energy, and right now we're looking between a C and D, the resistor. The internal energy is equal to the heating plus the electrical transmission plus the electromagnetic radiation. That's for the resistor. If you look at the whole system, the potential energy, the chemical potential energy, that's why it's U sub C, that comes from the battery. Now, again, this is the whole system. The chemical potential energy plus the internal energy is going to equal to the heat and the electromagnetic radiation. Now, there is no ET, there is no electrical transmission, because the resistor is internal to the system. But that's the what we're going to base it on. Here they're showing you a heat sink. When you have a lot of transmission, if you were to those of us that were nerds way back when used to operate our computers without the cover. I was one of those, because we were always changing out cards, data acquisition cards, and whatnot. And you would see these heat sinks on those, particularly on the microprocessor, and you didn't touch them because they were typically very hot. But that's a heat sink, and it just radiates. It radiates thermal energy to the air around it. And typically there was a fan blowing. I mean, not so much. I mean, all I have is my laptop, so I haven't had a desktop computer in a while, but they used to be pretty noisy with the fan blowing. As a matter of fact, if the fan started blowing, that usually meant trouble. So we're going to continue with electrical power. The direction, again, the direction of the effective flow of positive charges clockwise. So the change in electrical potential, or the rate of change of electrical potential, du dt, is equal to the change in the charge times delta v. The charge dq dt is equal to current, so that's equal to I delta v, and that's the power. So the power is the rate of change. Power is the rate of change of the electrical energy. So power is equal to the current times the change in potential, delta V, the voltage. So power equals I delta V. Now, if you recall from the Ohm's law, I is equal to delta V over R. So power can also be expressed as delta V squared over R, or if you consider delta V is equal to I times R, then power is equal to I squared R, and that's what we have here. Power is equal to I squared R, and it's also equal to delta V squared divided by R. And you can get these just from knowing Ohm's law from the previous a couple of sections ago. Let me see where I'm at here. So the rate at which the potential energy of a system decreases as charge passes through the resistor is the rate at which the system gains internal energy in the resistor. And the power is represents the rate at which the energy is delivered to the resistor. Okay, let's see. Now, electrical power lines. Now, if you read the intro, there was a question as to why they use these power lines, and do they use high voltage or low voltage? Well, the real power lines have resistance, and the fact that power is equal to I delta V, you can transmit power using high currents and low potential differences, or low currents and high potential differences. Well, the utility companies decide to use low currents with high potential, so that you have a power equals I squared R. The resistance of the wire is fixed at a relatively high value for economic considerations. So the I squared R loss is reduced by keeping the current I as low as possible. And you transfer the energy at high voltage, typically about 4K or higher, 4K volts by a transformer. We'll get to transformers later and see how you can, using a number of turns, increase or decrease the voltage and the current. Okay. And I think that's it for this chapter. We'll end it right here.